Hello and welcome to the Chapter 4 podcast on Section 4.3. Today we're going to be talking about Section 4.3, which deals with acid-base reactions. Now, one thing to kind of keep in mind is that we're probably not going to answer all your acid-base questions here. Later on in the course, we're going to spend a lot of time on acid-base reactions again in a lot more detail. But right now we're just talking about it from a solution stoichiometry point of view. So you'll get a little overview on this part of the course, but later on we'll go into more detail. Acids are basically substances that form hydrogen ions in solution. Sometimes we call them H pluses, and other times they'll be referred to as protons, but they're always the same thing. Acids are unique in the sense that they undergo solvation like ionic compounds do to form H plus cations, but notice that these are basically all nonmetals, so that's what makes it slightly different. Different acids can ionize to form different numbers of hydrogen ions. There are acids that are monoprotic that yield one hydrogen ion per molecule, like HCl. Sometimes we have acids that are diprotic that can give up two hydrogen ions per molecule, and sometimes we can have three. And when we have that, like with phosphoric acid, that's a triprotic acid. Bases you can think of as the flip side of acids. These accept hydrogen ions and react with them. Usually when H plus reacts with the base, we're talking about a hydroxide ion that it's going to react with. And you could imagine that you'll form water when this happens, but we're skipping ahead a little bit. A lot of bases have hydroxide ions in them. These are common bases, the sodium hydroxide, potassium hydroxide, and calcium hydroxide. But what's interesting is that compounds without hydroxide ions can also behave as bases, and we'll talk more about this later in the course, but this is also something that can happen. So sometimes what it does is instead of providing hydroxide ions by directly solvating hydroxide anions, what happens, it'll combine with the water that it's dissolved in to make hydroxide ions. And so the most common example is ammonia. Ammonia will react with the water it's dissolved in to produce ammonium cations and hydroxide anions. So this is how it's able to act as a base. Most bases are weak electrolytes, which just means that they don't dissolve in water very well. There are strong bases and strong acids. There are not that many of them, and you should probably memorize them because strong acids basically are strong electrolytes, and they completely ionize when dissolved in water. Anything else that is not on this list is considered a weak acid or a weak base, and these are weak electrolytes. And what that means is that they do not separate, dissociate completely when dissolved in water. And base is the same thing. The most common one again is NH3. So what that means is when we do net ionic equations for weak acids, we will not dissociate them even though they're aqueous. Identifying strong and weak electrolytes. Again, if you know that it's a strong or weak base, that can help, or for strong or weak acid as well. So if you're looking at ionic or molecular compounds, if it's ionic, it's going to be a strong electrolyte. Molecular, if it's an acid or base, it may or may not be strong or weak, depending upon what kind of acid or base it is. Okay? If the molecular isn't an acid or a base, then it's a non-electrolyte. So this is kind of the thought process we go through if we're trying to define whether something is an electrolyte or not. Strong or weak as well. Here are the general properties of acids and bases. So I'll let you read these. These are some basic things. These are just basic common things. Acids, conduct electricity, turn litmus paper red, they taste sour, they react with active alkali metals to basically give off hydrogen gas, and they'll react with bases and they'll neutralize through them. And then bases are the same kind of thing. Conduct electricity, they turn litmus paper blue, bitter taste, feel slippery, and react with acids to neutralize their properties. And they're both corrosive and dangerous in concentrated forms. When we mix acid and bases together, they will neutralize each other, and we call these a neutralization reaction. The products will be salt and water. A salt basically is just any generic ionic compound. Here's an example with magnesium hydroxide and hydrochloric acid. So we get water and magnesium chloride as an example. Magnesium hydroxide, again, is a solid. It's not soluble in water, so that's why it's written in this fashion. And then what you see underneath here is the net ionic equation. But it won't always be like that. Another neutralization example, let's say we are mixing carbonic acid and potassium hydroxide. Remember your naming rules for acids. Carbonic means that it should have been, the anion is carbonate. So H plus and HCO3 minus will form H2CO3. Potassium hydroxide will combine, will be K plus and OH minus to form KOH. Again, this is like another special kind of metathesis reaction where the H plus is going to react with the OH minus, the K plus is going to react with the carbonate. We have our reaction here. The net ionic equation, remember, because carbonic acid is a weak acid and a weak electrolyte, we do not dissociate it. Whereas the KOH we do separate, and what results is only the potassium as this lone spectator ion. Sometimes acid and base reactions will result in the formation of a gas. So this is when we don't have OH minus and H plus. Sometimes we'll have sulfide ions instead. And whenever you get H2S as a product, it's going to form a gas because it has a low solubility in water. Again, this is important for the reaction portion of the AP exam. Also, carbonate ions will also are unstable as well. They'll immediately decompose into water and carbon dioxide gas. So that's something also to keep in mind whenever H2CO3 is a product. Now if it's a reactant, you don't have to worry about it, only when it shows up on the right side of the equation. And that's it.